Welcome everybody. My name is Sam. I'm the session chair for this session, and the PC chair. But anyway, so I'm very happy to introduce Wenhao Tang from University of Edinburgh. He'll tell us about freezing bidirectional typing.
Thank you for the introduction. So I'm going to talk about how to freeze bidirectional typing, and I'm going to introduce a new approach called Frost, which focuses on doing bidirectional type inference for first-class polymorphism. So what is first-class polymorphism? Like, as many of you may know, there are some different forms of polymorphism. Like, they are different in where quantifiers can appear and which types can use when we do instantiation. So the most simplest one is the net polymorphism or pre-next polymorphism, where we only have top-level quantifiers, and we can only use modal type to instantiate type. For example, the classical polymorphic identity type. And we have higher rank polymorphism, where quantifiers can appear anywhere, but we can still only use modal types to instantiate a polytype. For example, here we have a function which takes another polymorphic function as an argument. And we have first-class polymorphism, which is the same as higher rank polymorphism that quantifiers can appear anywhere. And we can also use a polytype to instantiate another polytype. So suppose we have a single function which is polymorphic, it creates a list, and we have the identity function. We can do the application single ID to have a list of polymorphic identity function. And so we focus on first-class polymorphism, and by type inference, we want to infer where to introduce quantifiers. Like if there is a function from x to x inside the program, whether or not there should be a quantifier outside of this function. And we want to infer where to instantiate the quantifiers. Like if there's a variable ID in the program, whether or not we should to instantiate this identity polymorphic function. And if we do instantiation, which polytype we should use. And also for an anonymous function, if the parameter is not annotated with its type, which polytype we want to use for the parameter. But unfortunately, for type inference for FCP is undecidable. This is a well-known result in the literature. And because there is an undecidable problem, there are lots of different approaches in the literature using different intuitions and heuristics or algorithms to approximate type inference for successful polymorphism. So why we want yet another new approach? Our initial motivation is to do better type inference for modal effect types, which is a new effect system based on multimodal type theory. And I'm giving a talk on Saturday morning in Uppsala. So the key observation here is that type inference for modal types is very similar to type inference for first-class polymorphism. So as I have shown before, for first-class polymorphism, we want to infer where to introduce and instantiate quantifiers, and when doing instantiation, which polytype we use. For function parameters, which polytype to use. For type inference or modal types, we want to infer where to introduce and instantiate or introduce and eliminate modalities. And when we are instantiate a polytype, which modal type we can use, and for a function parameter, which modal type we can use. Yes, so we observe that the information flow between we observe that bidirectional type information flow is very useful to answer these questions. But many existing approaches do not make use of this information as much as possible. And in particular, let's consider a function application M2N. There are two different directions of flows from M to N or from N to M. And so what we want to do, and we want to make use of both of these directions. So we propose Frost, which allows the information to flow back and forth between functions and arguments. And we introduce a freezing operator, which is used to control the direction of information flow if there is no best choice at all. It is called frost because frost forms when marble flows to colloidal surfaces and freezes to acidic crystals. So I'll start with introducing the different directions of information flow in existing approaches. So first is to flow from the function to the argument, which is the most common approach in most bidirectional type systems. So for example here, if we want to infer a type for for m applies to n, we first infer a type for m, which is a, and then we instantiate a to a function type whose argument type is a1, and use the type a1 to type check the argument. As an example, we can use this information to know whether or not we should introduce some actual quantifiers to the argument. See that we have a poly function which takes a polymorphic function and returns int, and we apply poly to fun x to x. So first, we infer the type of the function, which is poly, which has this type, and then we use the argument type of poly to type check the argument from x to x. And because we know from x to x should have type for all a dot a to a, we know that there is an implicit introduction of this quantifier. As another example, flowing from function to arguments also tell us which polytype to use for function parameters. So supposing we have another function poly2, which takes a function that takes a polymorphic function, and we apply poly2 to fun x to 42. So first, we infer the type of poly2, which is this type, and we use the argument type of poly2 to type check fun x to 42, which tells us that for the argument, its parameter x should have the polytype for all a dot a to a. And moreover, this information flow also tells us if we want to do some instantiation, which polytype we can use. Supposing we have a poly3, which takes a list of polymorphic identity function and returns int. And we have nil, which is the empty list, polymorphic empty list. So we first infer the type of poly3, which gives us this type, and use the argument type of poly3 to type check nil. Because nil has a polytype, we know that we should instantiate it. Yes, we should instantiate nil, and we should instantiate the variable b with for all a dot a to a in order to give the argument the type list of for all a dot a to a. So these are three examples of flowing from functions to arguments. And there's another direction of flowing from the argument to the function. So this is typing rule in the paper that arguments go first. In this paper, in addition to a normal context gamma, we also have another context, which is a list of the argument types. So when we want to type check, we want to infer the type of m applies to n. We first infer the argument type A and append this type A to the new context for m, so that when we are inferring the type of the function, we can make use of the fact that its argument should have type A. And here is one example which tells us how to instantiate a function. So suppose we have a head function which takes the head element of a list, and we have a list of polymorphic identity function. So first, we infer the type of the argument, which is list of for a dot a to a, and this information is propagated to the function head, which tells us that we should instantiate head with for a dot a to a in order to make the argument type of head match the real type of IDS. And as another example, this direction of information flow also tells us which type to use for function parameter. So we have IDS again, and we first infer the type of the argument, which is the type of IDS. And this information is propagated to the function, which tells us that also the function is just an anonymous function from x to x. And we know that its argument should have type list over a dot a to a, which is exactly the type of the argument x. So we have seen so we have seen that in previous works we can have one direction of information flow. The question is, what if we want both of them? And here is one example where having both directions is important, where we apply a function foo. It is a polymorphic function. It takes another function from b to list over b and returns int. And we have IDS. We want to apply foo to another function that returns IDS. So if we first flow from the argument to the function, for which we want to pass the type of IDS to the function foo. And then, since we know that the function foo should take another function whose result type is the type of IDS, we should instantiate the type variable b with for all a dot a to a. And after this instantiation, the information then flows from the function to the argument. And we use the argument type of the instantiate foo to type check the argument, which tells us that the argument x of the argument from x to IDS should have type for a dot a to a. So for this example, we rather want both directions of information flow, but previous to typing rules cannot type check the example, because what we are doing here is we only propagate the type of IDS to foo instead of the whole type of the argument. So our idea is that we use skeletons, which are types with some ghosts, which represent unknown information, to represent a partial type information, and having a typing rule starting from n, starting from the argument n, going to the function m, and then going back to the argument n. So here is the same example as we have seen before. So we first infer a skeleton for the argument. For this argument, its skeleton is this. So we have, so a ghost represents unknown information because at this stage, we do not know which type should be the parameter of from x to IDS. So it is a ghost. And we also have two ghosts followed by a dot, which are universal ghosts, which represent some unknown list of quantifiers, because there could be some generalization or type abstraction later, which we don't know now. So we put some universal ghosts to represent that information. And we have the property that the skeleton of a term matches any of its possible type. This is very important to avoid rejecting any valid type for a term. And then, instead of passing the type of the argument to the function, we pass this skeleton to the function. And based on this partial information, we still know that we should instantiate the type variable b of foo with for all a dot a to a, because this skeleton tells us that the result type should be list of for all a dot a to a, which should match list of b. And then we can use the argument type of foo goes back to the argument, which tells us that the argument x should have type for all a dot a to a. Yeah, and so this is the core idea of how we support both directions, and here is more details on skeletons. So, like here we define type AB like standardly with variable A, unit type, a function type A to B, or a polymorphic type, and we define skeletons almost the same as types, but with ghosts and universal ghosts, which represent unknown type information and unknown quantifier information, respectively. And we also have a set of skeleton inference rules, which I'm not going to show here, but they are very similar to the typing rules. And they allow the skeleton information to propagate through the program structures. For example, if we have a pair of functions from x to x, its skeleton is a polymorphic pair of two polymorphic functions. But that is all. That is all the information we know. We don't know anything more, like what should be the type of the x, or what should be the type of the result of the function. And also, if this pair appears inside some net expression, then its skeleton is still the same, because the skeleton of the result of this net expression just propagates through the program structures. Yeah, and another question is, what should be the skeleton of a variable? So for example, if you have a variable x or type A in the context, we really want a skeleton that is compatible with arbitrary instantiation and generalization of this type A. So for example, for ID, we want a skeleton like we want a skeleton that matches with arbitrary polymorphic function, and for pair, we want a skeleton that matches with arbitrary polymorphic function. Sorry, this is a typo. But here is a typo. But we want a skeleton that should match with arbitrary polymorphic function from ghost to a pair of ghosts. So we have this meta operation hunt, which just does instantiation and generalization, but not with concrete types, with ghosts instead of concrete types. So if there is some type quantifiers, we instantiate with a ghost, and if there is another universal ghost, we just animate it, and when we reach a guided type, we introduce a universal ghost. So which is consistent to the definition of hunt, because now there are ghosts appearing in the result. Yes. And another question is, the skeleton may not be as informative as we want. And there is a very simple example to see why. So if you have a single which creates a list and the identity function, so by default, what we have enforced is that we'll infer a skeleton for the argument ID, which is ghost to ghost. And then we'll use this pattern to get the instantiation of a single. But however, this skeleton is very useless. It doesn't tell what kind of a polytype the argument should be. Well, in order to make the type inference deterministic, we have to guess a modal type here instead of some arbitrary polytype. So we can only instantiate single with some modal type tau to tau. And then we use tau to tau to type check ID. So by default, first gives us a list of tau to tau for some modal type tau for this program. But however, if all the information goes from the argument to the function, we actually can have the type list of for a.a to a, which is a more informative type. To see why, we have the argument has type for a to a, which is passed to the function to get its instantiation, which tells us that the argument variable A should match the polytype for all A dot A to A. So we can do a polymorphic instantiation for single. Oh, sorry. Yes, so in order to allow first to also give the type list of all A dot A to A, we introduce a phrasing operator inspired by phrase ML. So for this program, we can write a user annotation to phrase ID, and by phrasing it, the skeleton of ID is not ghost dot ghost to ghost, but its type for all A dot A to A. And yeah, so phrasing term means its type can never be influenced by its context. And we can use its for type to get the type inference of the outside. So this type is passed to single, which tells us that we should do a polymorphic instantiation for single. Yeah, and then the polytype for all A dot A to A also, of course, goes back to ID. Yeah, and here is one more example, which is combining a more complicated argument with phrasing. So first, we do a skeleton inference for the argument, whose skeleton is a polymorphic pair, whose first component is some arbitrary polytype, and the second component is for A dot A to A because ID is frozen. And then this skeleton is passed to choose, which tells us that we should instantiate choose with for all A dot A to A because the second argument of the pair has this type. And then afterwards, the argument type of the instantiated choose goes back to the argument, which tells us that the first component of the argument from X to X should have type for all A dot A to A. So there is an implicit introduction of the quantifier A. Yeah, and here is a table of some examples from previous papers comparing first, which is the first column with some other existing approaches. And I'm not going to dive into the details of this table, but as we can see, first performs okay in most of these examples. Yeah, and so what I have seen so far is what we have at the point of submitting the extended abstract. And after that, I realized that there's some excellent work on colored local type inference 20 years ago, which seems to provide a way to give a much better declarative representation of first. So since we are only caring about inferring polytypes, we have two different colors for quantifiers. One is in blue, which means they are inherited from the outside, and the other is in red, which means they are synthesized from inside. So for the previous typing rule of function application that I have shown you, it is first infers type of skeleton of the argument, goes to the function, and then goes back to the argument, which is intuitive, but it is kind of algorithmic because it more or less describes how the algorithm should do for a function application. But with colors, we can give a much nicer rule, like this, where A tilde means to reverse the color of A. And the idea here is that for the type A of the argument, all red quantifiers are those we synthesized from N, so they can be used to get the instantiation of M. And all those blue quantifiers in A are from outside. They are information that are provided by M to N. So we can use colors to represent this. We can use colors to represent the information flow of these two directions simultaneously. Yeah, and so this is still work in progress. We have a declarative specification based on ghosts and skeletons, as I have shown. And we have a more declarative specification using colors. We are working on proving a simple sound accompanied type inference algorithm for it. And this algorithm is already implemented in some toy language. With support for both first-class polymorphism and for modal effect types. Yeah, and I think my takeaway is we should allow type information to flow bidirectionally, and we do so via ghosts. And if there's no best choice between these two directions, we can phrase it via phrasing. Yeah, thank you.
Okay, we have time for a few questions. We have a mic right here if people would like to come up for questions.
Hi, thanks for the talk. You had that big table of examples.
Yes.
How many of those examples had to be modified with freeze annotations?
This is a very good point. So the left part of this table are taken from existing papers, and I think this is probably the only one that require phrasing, which is not supported by the other approaches we are comparing with. Yes, and the right part is some examples that we made, with a few of them requires phrasing. So I guess the intuitive answer is that in most of the cases, phrasing is not needed. But when we want some more fine-grained control on the direction to make some programs that are very hard to type check, then we can use phrasing to do so.
Sure, thanks.
Any more questions for Wenhao?
I just had a quick one. The last example.
Last example.
Yeah. I was curious if it still worked if I froze the left-hand side and left the ID unfrozen. No, choose with a function. Choose with an this one. Yeah, if I'd frozen the other side, does that work? It was a little unclear to me what exactly you freeze at. Whether you generalize and then freeze, or whether you're just going to freeze the ungeneralized type, or whether you're even syntactically allowed to freeze a constructive form.
So if choose is frozen, then it is ejected.
No. The fun x to arrow x. Can I put an ice cube around that and then not around ID? Because you know.
So intuitively, freezing term means its type must be what we can infer from inside of this term without relying on any information from outside. So freezing from x to x will give us an arbitrary modal type tau to tau.
Okay, not for all alpha. It's not the most general type that you're freezing.
Yeah, so there's no generalization before freezing.
I see. Cool. Thanks.
Okay, let's thank the speaker and we can get the next one up.